My name is Luis Joglarongay and I'm a software engineer and audio scientist working at Sonosuite in Barcelona. I also recently graduated from a Master's in Sound and Music Computing offered by the Music Technology Group at the Universitat Pompeu Fabra, also in Barcelona. At Sonosuite, we offer a wide label, flexible, scalable and affordable digital music distribution software as a service. The company's vision is to empower media creators to develop their catalog and manage the distribution, marketing, licensing, and royalties accounting activities. I am part of a team in charge of researching new ways to offer better services directly related to the music our clients trust us with, so to distribute channels like Apple Music, YouTube Music, Spotify, and many other channels around the world. Our goal is to develop state-of-the-art technologies in the digital music industry and put them in the hands of our artists and clients. As part of our efforts for providing tools to help artists improve their submissions to the channels, we have collaborated in a research project with the Music Technology Group of the Universitat Pompeu Fabra, in which we have developed algorithms to detect audio quality problems in the audio masters that the users upload to our platform. This way, if there is any issue, they can fix it before sending it. The first results of this project was presented in a paper at the Audio Engineering Society in Dublin in March 2019. You can find the reference paper linked at the supporting documents. The algorithms developed, which I will present in a moment, are included as part of Essentia, an open source C++ library, also with Python bindings that you can use for any kind of music analysis, description and synthesis software that you want to develop. After this project was finished, now as part of my master thesis, we started working on porting Essentia into the web world. While the MTG started working on compiling Essentia using WebAssembly to make it work as a JavaScript library, I focused on making sure that the audio quality problem algorithms were working fine with the Web Audio API to make it work in JavaScript. That is what I'm going to show you today. Let's briefly introduce the algorithms that you can use to detect audio quality problems, and as I mentioned before, remember that these algorithms are part of Essentia, a C++ open source library that you can also use in Python and in JavaScript. These algorithms are divided in 6 groups, the first one being incorrect margins. As you can see in this image, both excessive silence or insufficient silence at the beginning or the end of the song are the issues that you can detect. These algorithms are called start-stop silence and start-stop cut. The next group will be phase-stereo problems. In this case, you can detect both phase problems and FalseStereo problems. Following would be the audio artifacts problems, which are the most common problems that you can find in music files. These being burst noises, discontinuities, gaps and clicks, and you can also calculate the signal-to-noise ratio of your audio files. There is also a hum detector algorithm that will help you analyze if your song has hum noises, which are very typical of analog recordings. There are 2 loudness-related algorithms. The first one will allow you to calculate the loudness following the EBUR 128 standard, and the second one will allow you to see if your audio has any saturation problems. The last one is the TruePeak detection. The algorithm is TruePeak Detector, and it will help you detect if your audio is clipping. Now I'm going to show you a series of code in which we are going to use 2 of these algorithms, start and stop cut and saturation detection. Using these 2 algorithms, you will see how you can use any of the other ones to detect all of these audio problems in your files. I'm going to present 2 different ways of using Essentia.js. The first one uses the main library by loading it using the HTML script tags using a CDN URL. The second one is using a custom structure. This second way can be very useful if you want to use any algorithms from Essentia in a particular way and without loading the full library. More information about how to create your own custom structures can be found in the GitHub of Essentia.js. You have the link in the supporting material. Just a small disclaimer, remember that Essentia.js is a work in process and it is not ready to use in production services. However, let me encourage you to use it as much as you can in your personal projects and help us to improve it. Now let's start with the code. In this application, we are using Essentia.js together with the Web Audio API and the Canvas API to show in the browser the audio quality problems detected together with the waveform of the audio. This is the final result in which we can see highlighted the issues detected. We have the saturation problems marked in red and a cut at the end of the sound marked in blue. To do so, we are going to use a very simple JavaScript structure in which we are going to create an app object from which the rest will follow. Remember, this workshop is just to show you how Essentia.js works. Do not take it as a best practices guide to follow. You can use the library in your code as you see fit. Also, the HTML file is very simple, with just a text asking us to click and the script tags loading Essentia. To begin with, we are going to create an event to capture when we click in any part of the document. This will then trigger a reaction chain to load the audio and compute the quality algorithms. Let's now create the createAudioContext function to quickly check that the event is working. We can set a control log just for this purpose. We now go to the website, reload the code and click, and we can see the log in the console. As previously mentioned, in this application we are going to use the Web Audio API to be able to load an audio file and access its samples to use as inputs for the Essentia.js algorithms. So the first thing we need to do is create an audio context from the Web Audio API. Let's change this log so we can use it later. And now let's create an attribute to have access to the audio context in the rest of the app. Here I want to have an if to check whether we have already created the audio context, and in this case exit the function. Now let's load the audio context from the window. This block of code will help us with the different browsers. Now finally we have access to the Web Audio context and we can create an instance for our application. Otherwise, we will throw an alert. Let's print the audio context in a console log to check it works. So now we can reload the code and see the audio context in the log. Once we have the audio context loaded and an instance created, we can load an audio file and access its data. Let's create another attribute for the audio buffer. This will then be assigned by calling the function loadAudioTrack. Let's create then this function loadAudioTrack, in which we use the function fetch to load an audio file from a URL. We then need to add the URL of the audio file we want to use in this options object that we pass to the app. For this function to work asynchronously, using this await statement, we need to make the parent function also asynchronous. Now we are going to access the array buffer of the response, and as final step, we can return the audio data from the array buffer using the decode audio data from the audio context. So now in this audio buffer, we have the audio data from the file we want to analyze. Finally, let's have an attribute called left channel, where we can have the audio samples of the left channel of the audio, as we only are going to use one channel for this application. We can access the samples from the getChannelData function from the Web Audio API, using 0 for the left channel. We want left channel to be an attribute of the app. Now that we have loaded the audio we want to work with, what we can do is to show its waveform in the browser. To do so, we're going to use Canvas API. So let's have an attribute Canvas, and the function createCanvas with a log to see if it gets there. We are now going to check again if we have created our canvas context before, and if so, we can exit the function. Now let's create a DOM element canvas to render our waveform in. This element needs to have the width and height set. Now we can get the element with the text from the initial DOM and replace it with the new canvas element. Finally, let's have in our canvas attribute the canvas 2D context so we can render anything in it afterwards. Now this function is created, we can call it from our main function, that is create audio context, with the arguments width and height from our options object. Of course, we have to add these width canvas and height canvas options to the list. As width, we are going to set the width of our body to use the full available width of the browser, and we can have a height of 300 pixels. Now we can go to the website, reload the code, and we can see how when we click, the text is replaced by a canvas element. Now that we have the canvas element together with the canvas context and the audio data loaded from the audio context, we can create another function to display the waveform of the track. I'm not going to explain every step of this function as it is out of the scope of this workshop. You can easily find documentation about the Canvas API and you will see it is very easy to understand. What this function does is to fill the background of the canvas with this almost black color and set this other blue color to be used by the lines that will conform the waveform of the track. Now we create a loop to draw as many lines as we set in this draw lines option by going all over the samples of the song and selecting one every line gap distance, and finally drawing a line from minus the value of that sample times half the height of the canvas to the same value in positive. First line in this function is clearRect. This line resets the canvas element so we don't overpose any drawing over the previous one. We set as values the corners of our canvas from 0, 0 to full width and full height. Then we call the display. As always, we have to add the draw lines option to the list. Afterwards, the restore canvas function, and finally the request animation frame with the same draw function as parameter, having this way a recursive function. Having this display track function ready, let's create the draw function that will be called every time canvas needs to be refreshed. First line in this function is clearRect. This line resets the canvas element so we don't overpose any drawing over the previous one. We set as values the corners of our canvas from 0, 0 to full width and full height. Then we call the display track function. Afterwards, the restore canvas function, and finally the request animation frame with the same draw function as parameter, having this way a recursive function. Now add this same call to request animation frame function to the main create audio context to be called the first time. Okay, so now that we have the audio loaded and displayed, the next step would be loading Essentia to be able to use the algorithms that we want to compute. So let's create a function called load Essentia, where we are going to load Essentia from the Essentia module we get from the CDN URLs in the HTML script tags. We're going to load it asynchronously using this then statement. Afterwards, we assign the Essentia into an attribute of our app to have access to it everywhere. Once the Essentia is loaded, we can call another function to compute the start-stop-cut algorithm directly from the library. we create the compute start-stop function, where we call from this.essentia the start-stop cut algorithm, using as an input the left channel data, adapting it to what Essentia needs by using the array-to-vector Essentia function. Let's assign the results to an object with the form that is needed by the Essentia algorithm. Let's create it as an attribute. Now we are going to create a function to draw these results. Let's call it draw start stop cut. Here we checked if there are any positive results for the beginning or the end of the track, and if so, we create a loop to draw 5 blue lines instead of just one at the position we have found the issue. This way it will be more noticeable. In this second case, the lines will be drawn at the end of the canvas width. Let's create a function called drawLine that will help us to draw the lines in the canvas. Now we can call this function from the draw function to render over the waveform the issues found. So now we can go to the website, load the new code, and when we click, the algorithm is computed and the results are shown. We can see how at the end of the file we have a blue mark indicating that there is a cut. So we are arriving at the end of our application. We are now going to load a custom extractor that we have created following the instructions that you can find in the Essentia.js GitHub. You can find the link in the supporting material. We have loaded these files into our application in the folder extractors-saturation, and therefore we can import the module Essentia Wasm from there. We will need an attribute to store the instance from this extractor, from which we will call the saturation algorithms, and also another one for the results. Now we can create a function load saturation extractor where we can create the instance of the extractor with the frame size and hop size parameter values and assign it to its attribute. Then, following the steps we did for start-stop cut, let's create a function to run the algorithm called compute saturation. Here we will run the algorithm with its functions compute start and compute end, and save the results in the object assigned to the attribute saturation results. Finally, let's code the function to render these results. Draw saturation start. In this case, we are going to use the start values as these are sufficient for our purpose. We don't need to know exactly where each saturation event ends. We can assume that drawing a red line for each start event will give us a quite valid idea of the issue. So we check if there are any results in the start element, and if there are, we draw a line in each of these positions by calculating the x-axis pixel position from the time in seconds. And finally, we can load the finished code and see how, when we click, the song is loaded. Both algorithms are executed and the results are shown in red and blue over the waveform of the audio track. So we have seen how Essentia.js works together with the Web Audio API and Canvas API to show in the browser the results of the algorithms together with the waveform of the loaded track. We have seen a little overview of the algorithms to detect audio quality problems that you can find in Essentia, and we have shown 2 different ways of load Essentia.js into the browser. I hope you find this workshop useful and that you start using Essentia.js into your personal projects. And remember, you are more than welcome to collaborate with us into improving this library. Thank you very much.